This video will focus on the last problem type, which is being able to solve for a heat of reaction giving standard heats of formation. So far when we looked at thermochemical equations, the enthalpy of the reaction was given to you. But there are times where being able to figure out what that heat of reaction is too difficult. Okay? Potentially you're looking at a reaction that takes too long to be able to quantify in terms of from start to finish. It's a reaction that's really dangerous. Okay? Too exothermic, too much energy produced, so you wouldn't want to do it. There's a lot of different times where we might not want to do it. And honestly, to have a table that includes heat of reaction for every single reaction you would encounter, that would be an absurdly gigantic table. Okay, so we just don't have every single heat of reaction for every single reaction that would occur. But what we were able and are able to figure out something called a standard heat of formation. So what is a standard heat of formation? It is the amount of energy, or the enthalpy change, to make 1 mole of that substance, okay, if it's at the standard state. And the standard state for this unit is room condition, which is about 25 degrees Celsius and 1 atm. Okay, so it's the enthalpy change, amount of energy per mole to make 1 mole of that substance. Sometimes to make the energy, we need the energy, and then it would be endothermic. Sometimes to make that stuff, we will release energy, and it'll be exothermic. But either case, it's the amount of energy it takes to take the elements and make them into a compound. There are lots of tables that include standard heats of formation for different compounds. And remember that heat of formation is due to the elements coming together to make that compound. So if hydrogen combines with oxygen, it would be the enthalpy change related to making water from hydrogen and oxygen. On this chart here it's basically like a bar graph of some standard heats of formation for some compounds. Okay. If you notice here, the top is positive enthalpies of formation, so these would be endothermic. They require energy to make them. And then the bottom ones are negative enthalpies, so these will give off energy as you make them. And if you think about stability of a compound in relation to enthalpy, I can tell you that those top compounds, those ones that have a positive enthalpy of formation, so they take in energy to make them, they are explosives. Okay? Because when you break their bonds and rearrange them, all of that potential is available to use. Those that have a negative enthalpy or a negative heat of formation, they give off energy to be made, and so they don't have a very big potential. So if you want to break those bonds, sometimes you'll need to put energy in to even break them. They don't have any energy available to use. So a heat of formation actually tells me a lot about the potential within the compound in terms of energy released over chemical reaction. Because if you have a positive enthalpy, then you will be releasing that potential when you break them. And if you have a negative enthalpy, you'll need that energy to break them. And if you look, most of our hydrocarbons are negative enthalpies, which is good, in terms of life, that you are made of hydrocarbons and those hydrocarbons have a negative enthalpy. So you would need a lot of energy to get your compounds apart. You would be very unstable if you were made out of one of those nitrogen compounds that could give off so much energy if you break them. One thing that's on here, but I want to highlight too, is that standard heats of formation for any kind of free element, iron by itself, calcium by itself, sodium by itself, or for your diatomics, HNOF17. Those are considered to be 0. Okay, there is no really formation happening there. Those are considered their elemental states. So our elemental states have a baseline of 0 heat of formation. Here's a table with some heats of formation. There's tables in your book, and on the test, any heats of formation you would need, I would give you. Okay, these are not numbers that you could make up. They're established numbers that you need to use. So here's your equation for how to calculate a heat of a reaction from heats of formation. What you do is you add up all of the heat of formations for all of your products, and you subtract away from that all of your heats of formation for your reactants. From that, then you'll get the overall heat for the entire reaction. So this should make sense. If we want a heat of reaction, we want to know over the course of this reaction how much energy is released or taken in. Whatever your heats of your products are, that's your end result. Okay? If your products have a positive heat of formation, you will have a positive heat of formation for them in the end. If they have a negative heat of formation, you will need a negative heat of formation for them in the end. Your reactants, though, the heat of formation for those are making them. And for your reactants over the course of your chemical reaction, you're breaking them. So let's say you have a reactant that has a positive heat of formation, meaning you have to put energy in to make it happen. If that's your reactant, it's going to give you that energy back out, which means we need the opposite sign, which is why they're negative. If you think about it another way, it's like whatever energy that you needed to begin with, you would take that away from whatever energy you ended with to get the overall sum of the energy. Okay? But again, your reactants is all about the fact that they're an opposite sign than what you had initially. So let's try this problem. This is the decomposition of hydrogen peroxide. It's a demo that we've seen before, and we know it's exothermic, which means we should end up with energy out in terms of our calculation, and it should have a negative value on it. So using a table that contains standard values for my heats of formation, I get that hydrogen peroxide has a heat of formation of negative 187.8 kilojoules. That means to make hydrogen peroxide, I give off energy, which means if I need to break it, you need to put energy in. Over here, same thing. This is for liquid water. The state of matter determines the heat of formation, so you'd have to make sure you get the right one. Again, this says to make water, I give off energy. To break water, I would need to put energy back in. I don't give you the heat of formation for oxygen, and that's because it's one of your diatomics, and diatomics have a heat of formation of 0. So to figure out what the heat of this reaction is, again, it's the sum of all of your delta H's for your products minus the sum of all your delta H's for your reactants. So you got to make sure you keep your signs straight. For my product then, I have negative 285.8 kilojoules per mole, but I have 2 moles of it in terms of this chemical reaction. So I would take that and multiply it by 2 to get the amount of energy it takes to actually make that. Oxygen 0, so I can simply ignore that. Then I'm going to minus away the sum of my reactants. And for this one, my reactant formation is negative 187.8 kilojoules per mole again. But now it's only 1 mole. So you don't really have to write this down, but just to remind you, you're going to multiply it by the number of moles that you actually need in the chemical reaction. That'll get rid of the mole part, so you just have kilojoules as your final answer. So to do this math, it's 2 times negative 285.8 kilojoules minus negative 187.8 kilojoules. And if I do that math, I get that my delta H of reaction for this reaction is negative 383.8 kilojoules, which is good. Energy out, which is what I'd expect because there was a heat released when we saw that reaction. And again, some of these numbers should make sense in that to make hydrogen peroxide, you release energy, so you need to put energy in to decompose it. And we've talked about the fact that hydrogen peroxide is in a brown bottle to keep the energy away from it so it doesn't decompose. And also we use a catalyst for this reaction to make this decomposition happen. Okay, so you have to put energy in. And the same with water. You release this to make water. To break water, then you have to put energy in. And we have to use a battery or some kind of energy source to break that water apart. So the signs on these heats of formation should make sense in relation to some of the other things we've seen. That's it for this problem type. You just need to know that it's product minus reactant. and how to use a reference table. So on the form, I'll give you some example problems to try this to make sure you can calculate heat of a reaction from the standard heats of formation. Have a nice night.